Last time we were working in 3.4 and we had taken a look already at all of the different algorithms. We had a few examples left to take a look at. I believe we're on example, it's called example 2, is that right? Okay. Example 2, I really want to change this name. I keep thinking every time I do it I need to change his name because I don't know how to pronounce it. Do you know how to pronounce his name? Jean? We'll say Jean. Jean saved $53.40 in 3 years. If he saved $95 per month in the first year and a fixed amount per month the last 2 years, how much did he save per month during the last 2 years? So this sort of draws upon what we did in problem solving in Chapter 1. It's definitely got some multiplication features in it, which is why it's occurring now again in Chapter 3. So what could you do to solve this problem? Okay, so you'd multiply 95 times 12. And why do you want to multiply 95 times 12, Carly?
Because that's how much you paid the first year.
All right, good. So this is year 1. 95 times 12. So, and we've got lots of methods for doing it. Just for fun, let's do the lattice method for 95 times 12 so that we can remember how it worked. A couple of you weren't here last time. So 95 times 12. I shouldn't have drawn it quite so boxed together up here. Okay, so each box is multiplication, so it's 9 times 1. It's not a trick question. What's 9 times 1? 9, thank you. It goes in the bottom box. 5 times 1? Still not a trick question, 5. All right, 9 times 2? 18. So the 1 goes in the top and the 8 goes in the bottom. And then 5 times 2? 10. So the 1 goes in the top and the 0 goes in the bottom. And then we add along the diagonal. So this is 0. What's 8, 1, and 5? 14, so we'll carry our 1. What's 1, 9, and 1? 11. So the number is 1140, right? So he made 1140 the first year. Now what would we do?
Subtract that out of 53.40.
Good, so that's going to give us what? I'm sorry, you're going to tell me the number. Why are we doing that? Let me say it that way.
Oh, because that's how much you made in the first year.
And so by subtracting it, what are we going to end up looking for getting? The second and third, yeah. So this is going to be our second and third year amount total, like the total from both those years. So what did you get when you subtracted, Katrina?
4,200.
Excellent. 4,200. Now what? Divide. What are we dividing by 2? Why are we going to divide by 2?
It's 2 years.
Okay, that's fine. We can do that. So if we divide by 2, what's that going to find for us? Okay, so it's going to find an individual year's savings, right? What could we do if we wanted to find the actual answer right now instead of dividing by 2? We could divide by 24. If we divided by 24, we would immediately find how much she saved per month, because 24 is actually the number of months in 2 years. So you can either do it in 2 steps and divide by, like you suggested, divide by 2 and then divide by 12, or we could divide just one time by the number 24 here. Is that okay if we divide by 24? Okay, so 24 goes into 42 how many times? Once. 1 times 24 is 24. And then we subtract. So what do we subtract when we do 42 minus 24? 18. Very good. 18. So then we bring down the 1 or the 0. So now I've got 180. Any guesses as to how many times 180 goes into 24 or 24 goes into 180? 7. 7 works. What's 7 times 24? It's 168. I'll help you out. What's 180 minus 168? 12. So now I've got 120. How many times does 24 go into 120? That's 5. So the answer then is $175 per month. So the first year he saved $95 a month, and then the last 2 years he saved $175 per month. Is that good? Okay, let's try another one. Dan, I can pronounce his name. Dan has 4,520. He has 4,000 pennies. Dan's got some issues. 4,520 pennies, and he's got them in 3 boxes. He says there are 3 times as many pennies in the first box as in the third, and there are twice as many in the second box as in the first. How much or how many does he have in each box? I think I should say many. How many does he have in each box? All right, suggestions. This is a problem-solving kind of thing. What are we going to do? What would you do? Can I draw a picture? Okay. I'm going to draw 3 boxes. 3 boxes, and I know some information about the boxes. It says there are 3 times as many in the first as in the third, and there are twice as many in the second as in the first. So it sounds like all of this is hinged upon however many are in the third box. Does it sound like that to you? I'm going to use a little bit of algebra with this one. Let's put X pennies in the third box. So X here is a number of pennies, and it's in the third box that I've drawn. So the first description says there are 3 times as many in the first as in the third. What does that mean? 3x in box 1. And then it says there are twice as many in the second as in the first. What does that mean? 6x in the middle, because I double what was in box 1. How can I use this picture then to figure out how many pennies he has in each box?
I can first box the 3x equals 4,520.
Not quite. We're going to set something equal to 4,520, but it's not just the 3x. Did you have an idea, Shelby? Add them all together. Why would we want to add them all together? Do you know?
So they equal 4,520.
They are going to equal to 4,520 when I add them all together. Remember what these x's represent. They represent just how many pennies there are. So imagine actually having a bunch of pennies all in these separate boxes. If I wanted to figure out how many pennies I had total, I could just dump all the boxes together. That's the same as adding them up. So I'm adding them together because I would essentially be combining all the boxes together. And they are equal to the 4,520 then. So then what is 3x plus 6x plus 1x, or plus x? That is 10x. And then we can divide. What is 4,520 divided by 10? 452. Now the question asked what? How many are in each box? So have I answered the question yet? Not quite. But I've answered 1/3 of the question, yeah. What is the 452 here at the end telling me? That's in box 3. So box 3 has 452 pennies. Now what? Would we divide by 3? Multiply by 3. Okay, there we go. Yes, multiply by 3. And that will give me which box, Audrey? Box 1. All right, so if you take 452 and you multiply by 3, 3 times 2 is 6. 3 times 5 is 15. 5, and we carry the 1. Why do we carry that 1 again?
Because one's
Right, the 1 is actually in the hundreds place, right? I mean, like it's actually the number 150 that we're doing, so we get 5 here. And then the 3 times 4 is 12, plus the 1 that we carried over, giving me 13. So there's 1352 pennies here. Oh, I'm sorry. Thank you. 1356 pennies here. And then I've got 1 box remaining. How do I find how many are in box 2? Right, so I can take the 1356 times 2. 2 times 6 is 12. Carry the 1. 2 times 5 is 10, plus 1 is 11. 2 times 3 is, plus 1 is, and 2 times 1 is. All right, so there are 2712 pennies in box 2. What can we do to check to make sure that we have a reasonable answer, or at least one thing that we could check? We could add them all up, and what should they equal?
45.
They should equal to 4520 if we add them all together. Any questions on this one? Okay. One last question, a little bit more theoretical. This is one of those, the student is a bright student, and so they ask things that make you think. I mean, this will happen in your career, I promise. It's happened in mine. A student observes that 39 plus 41 is the same as 40 plus 40. Is that true? Sure is. It's the same thing. And so they want to know if 39 times 41 is equal to 40 times 40. So let's first answer the question, is it equal? Are those two sides the same? No, they're not. It doesn't work. And you could actually physically multiply each side to show that it doesn't work, right? But let's actually show what's happening in terms of the math that's involved so that you can kind of have a sense of why it doesn't work. So the answer is that no, it doesn't work. Now, the reason that the first one worked up here is because 39 is really just 40 minus 1, and 41 is 40 plus 1. So you see you've got the minus 1 and the plus 1 that cancel each other out. That's why that did work. So if you think about it from that perspective down here and do the same thing, 39 would be 40 minus 1, and 41 would be 40 plus 1. And you can't just add the 1 and the negative 1 together like you could when it was addition. This is actually a problem that's a multiplication problem. So you would actually multiply this out, like FOIL it out. That's the phrase you've heard before. Or you would distribute it out. That's the phrase we've used in class. So you can take 40 times 40 plus your 40 times your 1, which is these two numbers multiplied together. And then you have your 40 times negative 1, that's the inside terms multiplied together. And then the last one, it doesn't look like a very good negative 1. Let's try that again. And then the last one is negative 1 times 1. Now, we actually do have a positive 40 and a negative 40 here in the middle that do add to 0, don't we? Yeah? And we've got that 40 times 40 that they thought that it might be at the front. But we've got something extra. At the end, we've got 1 times negative 1. So we end up actually getting that we've got the 40 times 40 minus the number 1 at the end. And as long as you can add and subtract a number 1, this will always be 1 different. So it actually is the fact that if you had the 39 times 41, that it's 40 times 40 minus 1. And if you did 29 times 31, it'd be 30 times 30 minus 1. It'd always be off by the number 1. And it's because of the distribution property that that's happening. Okay? So how would you reply, or what would you reply to the student? Well, you would tell them that it doesn't work, and you would multiply both sides together. Okay, that's what you would do with the student. And if they wanted to keep talking to you about why it doesn't work, you could show them the distribution property. It's not outside of the realm of things that they would be able to work with and understand. Okay? Any questions on that one? All right, one more on this slide. Very similar idea, and it carries on with what we were talking about. It says, another student then observes that when you multiply 39 times 41, you get 40 times 40 minus 1, like we just observed ourselves, right? This is yes. Yeah, okay. Y'all, I know, bear with me. We're almost done, I promise. Almost done. All right. He also found that 49 times 51 is 50 times 50 minus 1. And the example I gave just a minute ago was that 29 times 31 is 30 times 30 minus 1. He wants to know if the pattern continues. How do you respond? Well, it will continue. It will work. And it will always work as long as the numbers are 2 digits apart. Right? Notice all of the numbers that I'm giving the examples of, and that he as well, is that the two numbers, 39 and 41, 49 and 51, I gave you 29 and 31, they're all differ by 2. Right? They're exactly 2 numbers apart. So if you have two numbers that are 2 numbers apart, and I'm going to show you the algebra behind what's happening here. That is, if one number is x and the other is x plus 2. They're 2 numbers apart. Then when you multiply these together, you get x squared plus 2x. So far, so good? Now let's do what we've been doing with the problem. Well, what we've been doing is we've been saying we can increase one of them by 1 and decrease the other one by 1. Well, increasing x by 1 is x plus 1. Decreasing x plus 2 by 1 is x plus 1. They're the same, right? So you can actually multiply this out. And if you multiply this out, you get the x squared. The inside and the outside terms together, oops, sorry. The outside and the inside both give you x. And the last term gives you the 1. So this is x squared plus 2x plus 1. And exactly how much bigger is it than the first expression? 1 bigger. So when I add the number 1 and I subtract the number 1, in essence, I've increased the value by 1. It's exactly 1 too big when I do that. So I could do that, and then I just have to take the 1 off, which is what you're seeing happen up here, in order to find the correct value. I know that's kind of over the heads of what you're going to be working with some of these kids, most of your kids. There's going to be some kids going to have something weird, and you're going to have to show something real, or they're going to really have a frustrating time with you because they're going to feel like, my teacher doesn't know my math or something like that. They can't really explain why something's happening. So what I want you to take away from this example is that, not that you're going to recreate this example. I don't expect you to recreate this example for me right now, even on a test. That's not my point. Is that when you do have a student that asks you a question that's above the point where you're able to really explain why, that you have the resources to be able to find out why. Either you've got people that you can contact, either someone in a high school setting or in a college setting, or you have textbooks or Google that you can research to find out why something happens. Because it's going to be a lot better for your students if you're able to say, let me look that up and I'll let you know, and actually come back to them with an answer, than if you just say, it just always works that way. Have you ever had somebody tell you it just always works that way? It's a less than satisfying answer, isn't it? It really is. So keep that in mind when you're working with a student, that if you don't know the answer, that's okay, but that doesn't mean you're off the hook for finding the answer, okay? All right.